Hello and welcome to Non-IITN. In this particular lecture, we are going to talk about a few important problems on complex analysis from NBHM. Now, the plan of the lecture is as follows. We won't go through detailed solution of every problem because some of the problems are quite easy to handle regarding some of the concepts which you somewhat are already pretty much acquainted with. So we'll go through the problems one by one. The problems which I'll feel that these are the ones which a student can handle on their own, I'll just give the hint and leave it as an exercise, and the rest of the problems we'll deal with in details. So let us check the first problem here. Now this is a problem which you are pretty much comfortable to do. I'm just writing a few steps, few initial steps of the problem. See, so if I talk about the solution, just wait a second. So if I talk about the solution of the problem, then you have 1 over z minus 1 times z minus 2, but then you can write it as z minus 1 minus z minus 2 divided by z minus 1 times z minus 2, the usual partial fractions, which obviously there are certain conditions, but in the nicest situations it's you can actually do this. So divided by, so this becomes 1 by z minus 2 minus 1 over z minus 1. Now you are given that modulus of z is less than 2 and greater than 1, so just apply the inequality. So from here what do you get? You get 1 over mod of z is less than 1, and from here you get mod of z over 2 is less than 1. So from here you need to take minus 1 over 2 outside, so this becomes 1 minus 1 by 1 minus mod of z by 2 minus, and from here you need to take 1 over z outside, so this becomes 1 by 1 minus mod of z. And now just expand them, you're good to go. Okay, just expand this and expand this, and then you're asked to find a3, so that should be the coefficient of the third part of the Taylor part, right, of the analytic part of the function of the series. Let us move on to the next question. So it's saying that consider the Taylor expansion of the function 1 over 1 plus x cubed in powers of x minus half. Okay, we are being asked what's the radius of convergence of the series. Now this problem is pretty much seen in a few consecutive years. We'll get similar problems at the end of this problem session as well, I hope, because I remember I have seen this problem multiple times. Not exactly this problem, but problems similar to this. So the way to do this is that, so the concept here you need to talk about is that the radius of convergence is the minimum distance between the center of expansion, that is the center of the series, and singularities. So it's the distance between it's the distance between the center of the series and the singularities. So you are asked to expand this particular function in terms of of the power series based on 1 over 2. So your center of the series, so here I have the center of the series to be 1 over 2. What are the singularities? So 1 over 1 plus z cubed is equal to 1. Okay, so this is basically given in terms of a real Taylor series, but nevertheless it won't cause a difficulty. So I wrote the theorem in terms of the complex power series, but nevertheless the same thing will happen here as well. So or probably did I copy this wrong? No, I didn't. Yeah, so let's just find the singularities here. So the singularities of this particular function will be 1 plus x cubed equal to 0. Now you are given a real variable, but you are nowhere mentioned it a real variable. So whatever you can do, what you can typically do, or what you can think of this problem is, you can just lift it up in the complex plane and work out there. Or typically you can think that you are working through this series in the complex field and draw conclusions there and be happy with that, because that's what we are going to do here. Because in some sense, this is an analogy between the Taylor series expansion over the real variable and the Taylor series expansion over a complex variable. That the only thing in the way you can try and talk about the radius of convergence is obviously the shortest distance between the center of the series and the nearest singularity. And the problem is that if you're strictly based on the real field, then all the singularities might not be available to you, but you can just lift it to the complex field and bring out all the singularities and then check out the distance between them. Ultimately the distance will come out to be a real number, and that's how you define the radius of convergence. Because on a basic note, if you have a complex singularity here as well, the function in some sense will fail there as well, though it's not available in the real field. So I hope you are getting to understand what I'm trying to say, right? So here what do you have? Let's see. So from this you can say that x is equal to -1, 1 by 2 plus I root 3 by 2, and 1 by 2 minus I root 3 by 2. So these are the singularities. Now what is the nearest distance between the center and these singularities? So the first distance is 1 over 2 plus 1, which is 3 over 2. The next distance would be root 3 by 2. Both the distance will be root 3 by 2, right? So the distance 1 over 2 minus 1 over 2 plus or minus I root 3 by 2 will be root 3 by 2, which is smaller. This is smaller. So therefore, the radius of convergence of this series should be root 3 by 2. Is it clear? So in this problem, what we typically did was we just lifted the notion to the complex field and solved it there. Okay, is it fine? You might also be a bit confused that why could we efficiently lifted it to the complex field. Let me just explain it like this. We know that the radius of convergence of a power series is given as the lim sup of the modulus of a n to the power 1 over n. And we also know about uniqueness of power series about a particular center. So the power series which is given to us, we are given a fixed set of coefficients which determine the power series, and the radius of convergence is a property of these coefficients. So it doesn't change regardless of whether you view the series on the one-dimensional real line or the two-dimensional complex plane. That was the exact thing which which you could have already analyzed in some sense. This was only possible because the thing which we were being asked to find completely depends on the coefficients, and the coefficients won't change on this lifting. Okay, fine. Let's move on to the next question. So the next question is actually a very good question, and most of the solutions which you would have find online or probably you could have tried and come up with were quite lengthy. But this problem is actually not based on a very lengthy procedure, but it's actually based on a conclusion drawn from such a lengthy procedure, which is as follows. See, remember this: if D is a domain, let's say, and f is a holomorphic function. F is a holomorphic function. Now we know that holomorphic functions behave as Mobius transformations, right? Provided that its derivative is non-zero, as we know. Nevertheless, if f is a holomorphic function, then if we denote D prime as the image of D, then the area of the image of D is given by the double integral over the domain D of the modulus of f prime z squared in terms of both the coordinates x and y. So this is what we call the theorem of area transformation. But the funnier part comes now, that the limit as r goes to 0, and the r is the radius of the domain. So we you can just think this to be a disk. Rather than domain, let me use the term a disk. Okay, and this is the radius of the disk. Okay, as r goes to 0 of the area of d prime over the area of d, this is nothing but the modulus of the derivative at z0 squared, where, now let me explicitly write the form of d, where d is the disk modulus of z minus z0 less than or equal to r. Okay. So this is the center of the disk. And once you put this, so this, the proof of this is quite long, I would admit, but this is the thing on which the problem was actually based. So therefore, what should our answer be? So limit r goes to 0, area of d prime over the area of d, this should be the modulus of f prime at pi by 4 whole squared. But then f prime is cos of z, so cos at pi by 4 is 1 by root 2, that squared is 1 by 2. So this should be your answer. I hope it's clear for everyone. Let's move on to the next problem. Okay. So this is the problem which is saying that find the real number a such that the integral over the contour mod of z minus I equal to 1 over the given integrand is equal to pi. This problem is actually quite interesting in the following sense. Let us first draw the contour here quickly. So what the contour is, let me change the color. Yeah, so the contour is, we start at z equal to I and we move for the radius 1. So this is what a contour is, right? Let me draw it a bit better. Yeah, this is in some sense what the contour is. So this is C. Okay, let me just take the conventional direction anti-clockwise. Okay, now when so the immediate thing which should sort of click in your mind to solve an integral problem are either the Cauchy integral formula or the residue theorem. Now obviously here you cannot observe how to use the Cauchy integral formula, because you have nothing to say about A, so you cannot say whether you have a singularity within the given contour or outside the given contour in that sense. But something which you can use is in the following way. See, there is one way of finding the residue of a function at some particular singularity. First of all, say what are the singularities of the integrand. So the integrand is z square minus, so singularities of the integrand will be followed from this. So from here you can say z is nothing but 1 plus or minus root over of 1 minus 4 times a over 2. So these are the integrands, right? Now there is one way to find the residue at some particular singularity for a rational function, which you can do it in this way. So if you have a function of this form fz over g of z, and you have a singularity at, let's say, z0, and you need to find the residue. So one way of finding the residue is given by f at z0 divided by g prime at z0. This is one way to calculate the residue of this function at z0. And observe that if I choose this to be g of z, and here you have 1, so if I choose this to be f of z, then on differentiating g of z, we do not have a anymore, right? So therefore we have the following. So therefore we can think of finding the residue in that sense. Okay, so the residue of 1 over z square minus z plus a at the possible singularity should be the same as 1 over 2z minus 1 at the required singularity. So I hope I'm making sense out of this. Right. So what should this be? So this is 1 over, you can just put this here, 1 over 2 times of this. So this is 1 plus or minus root over of 1 minus 4a minus 1, which is 1 over plus or minus root over of 1 minus 4a, right? And then what does the so what do we have now? So now I had that this integral should be pi. So by the Cauchy residue theorem, let us just keep both the signs for the moment, because ultimately we will be squaring it out to get the value of a, as we'll see, or at least we are going to take the modulus, or we are going to square, because we obviously need to square it out, because I don't want to keep the root, right? So by Cauchy residue theorem, what should I have? 2 pi I times the residue, which is 1 plus or minus root over of 1 minus 4a. Now you might argue that this is mathematically incorrect, because after all we take the sum over all the residues, so both of them might give me distinct residues. So for that you can just choose the functions one by one. You can just put plus ones and then check it out, or you can put minus ones and then check it out, or you can also try and get both the both the roots separately. But the problem here is we do not know whether which one belongs to which, right? So the only thing is, what we can do is that we can check what happens, right? Yeah. Yeah, so for the moment, yeah, so this actually brings up some serious problem. Okay, so let me just remove this part. I also make these mistakes, because I am just framing out these solutions here itself. So I often get confused. So let me try a different approach. But the way we are thinking, it will be the same. Okay, so the way we are thinking, it is 110% the same. What we can do is that we can go for the same thing, and we can just reverse the procedure in the following way. Firstly, so let me write this in the following. Let fz by gz be the integrand 1 over z square minus z plus a, and suppose I choose, let z naught be a singularity in the contour, or in the region, let's say. Okay, then the residue can be framed as exactly what I said, 1 over 2 times z naught minus 1. So by the Cauchy residue theorem, what do we have? 2 pi I by 2 times z naught minus 1 should be equal to pi. So these cancels out, and what are we left with? So I have 2 z naught minus 1 is equal to 2i. So therefore z naught is 2i plus 1, which implies z naught is, so 2 times z naught is this, so I have z naught is I plus 1 over 2, right? Now what we can do is that, now this z naught, whatever we got with this z naught, this should also be a root of this polynomial, right? Because after all, this z naught was chosen to be a singularity, and that is why we calculate the residue in the way. But after all, the singularity should be the roots of the denominator, and we know that if this is a root of the denominator, then its conjugate should also be a root of the denominator. Nevertheless, we do not require the conjugate to be a root of the, because it's not a real polynomial, we can say that. Let this be it. So now therefore I plus 1 over 2 whole squared minus I plus 1 over 2 plus a, this must be equal to 0. So from here what we can conclude, so if I just expand it out, so this becomes minus 1 plus 1 over 4, this is plus I minus 1 over 2 plus a is equal to 0. So these cancels out. Here we have minus 3 over 4 minus 1 over 2. So this gives minus 5 over 4, right? So we have this implies a to be equal to 5 over 4. Yeah, so this must be the answer, is equal to 5 over 4. Yeah. So there were the few mistakes which I, which I said, which you should not, in some sense you should keep in your mind. Is the first thing is that the first approach we followed, it was technically correct, but we lost our way because we were getting two distinct roots, and in that case I need to find the residue by adding up those particular roots, but we weren't in some sense sure whether the roots belong there or not. So what we started with is we assumed a singularity there, and we calculated what is the possibility for the singularity, and something which you can see is that this is inside the contour, inside the region which we were in some sense claiming, right? That was the thing which you need to keep in mind. That is the reason why we framed the overall concept from the backside. Moreover, the thing I misinterpreted was that, though it wasn't useful, but still I said it, that z not equal to I plus 1 by 2 is a root, so z not equal to I minus 1 by 2 should also be a root. That in some sense was not right. The reason being, first of all, it's not the conjugate, and secondly, if I have a complex root, then its conjugate is also a root. That holds only for real polynomials. Over complex polynomials, that's not something which we should be concerned about. Nevertheless, I hope we got the answer, and let us move on to the next problem. So the next problem is as follows. Let f from c to c be an entire function, and u and v are its real and imaginary parts respectively. We are given ux equal to this and vy is equal to this, and f of 0 equal to minus 1. We need to evaluate f of 2. Now, let me tell you one thing, solution. Now, one way which you can proceed is in the following way, that you are given ux equal to x square minus y square, and you are given uy equal to minus 2xy. Now, something which you can do is in the following way. Since you are given that it's entire, so it will satisfy the Cauchy-Riemann equations. And from here, you can integrate partially with respect to x to get a value of u. You can redifferentiate it with respect to y and compare to get the value of the constant which you will be getting. The constant would obviously be depending upon y if you integrate it partially with respect to x. And then you can use the CR equations to, because you have ux equal to vy, so this should also be the interpretation of y. And similarly, you can use the Cauchy-Riemann equations to get the interpretation for the partial derivative of v with respect to x from here. But there is a shorter method which probably it's called the Milne-Thomson method. Milne-Thomson method. And under the Milne-Thomson method, what we do is that we let phi 1 of xy to be the partial derivative of u with respect to x, which here is x minus y square, and we take phi 2 of xy as the partial derivative of u with respect to y, which is this. And then what we do is that we choose the functions by replacing x with the complex variable z, y replaced by 0 in both the cases. So we take phi 1 z of z0, we take phi 2 z0, and we frame this as f prime at z. Okay. Now this actually comes from the Cauchy-Riemann equations itself, and the fact that the derivative of a function is nothing but ux plus ivx. Okay. So it in some sense it comes from there itself. But nevertheless, you can take this to be a tool. Now, if you put it here, so you get z squared minus, so this becomes 0, so it's just z squared, right? So from here you get f of z equal to a simple integration z cube over 3 plus c. And furthermore, you were given that f of 0 equal to minus 1. So since f of 0 is equal to minus 1, you have c to be minus 1. So you have f of z equal to z cube by 3 minus 1. So therefore f of 2 must be 8 by 3 minus 1, which is nothing but 5 over 3. Okay, let us see the next problem now. The next problem says the following. Let D be a domain in the complex plane, A be a an element from the domain, fine, let f from D to C be a holomorphic function. Suppose there exists a number r positive such that the disk is contained in D, okay, and such that f of a is less than or equal to f of z for every, okay, fine, fine. Now, isn't this a direct application of the minimum modulus principle to say that minimum modulus principle? Because carefully observe what we have. So we are having a domain D. So this is a domain D. I chose a point A from here. I have a disk which is completely contained in the domain D. So I can now restrict my whole observation to this disk itself. And then what we are being said is that the modulus of f of a is less than or equal to the modulus of f of z for every z in this. So therefore, what does this typically saying you? Isn't this saying that a is a local minima within the disk? So by the minimum modulus principle, what can we conclude about this? Right? So either f at a must be 0 or it has to be a constant, right? The minimum modulus, by the minimum modulus principle, the only possibility for a minimum to be attained, minimum for the modulus to be attained, obviously, within the region is if it's 0 at that point. Otherwise, the minimum should be attained on the boundary. Otherwise, the function has to be constant, right? So either f is a constant or f must have a 0 at a. That should be the only, the only thing which you can say about f probably. Yeah. So the only conclusions which you can draw is that either a is a 0, obviously an isolated 0 because we are talking about a holomorphic function, or it has to be constant on the domain, right? Right. Yeah. Let's move on to the next problem. What is it saying? So let G star denote the set Z in C. Okay, so it's just the disk, punctured disk. It's just the punctured disk, and it takes all the elements in the complex plane except plus or minus 10. Okay. Which of the following is or are true? F has an essential singularity if at z equal to 0. Okay. Now it won't have an essential singularity at z equal to 0. That can be immediately concluded by the Casorati-Weierstrass theorem, right? Or probably the variant of it in terms of the Great Picard's theorem. Because let me just explain it a bit. This is actually, the option A can be treated in this way, that we know that if f has an essential singularity at at z naught, then f attains every single complex value with at most one exception. It can probably leave at most one point in any neighborhood of the singularity, in any neighborhood of the singularity, right? So therefore, if it would have had an essential singularity at z equal to 0, then it would have attained either plus 10 or minus 10, but it's leaving both plus and minus 10. So option A cannot be true for obvious reasons. If had either an essential singularity or a pole, it's again wrong because it can never attain the essential singularity. Option C is again correct. Right, option C is again correct, and option D say f has neither an essential singularity nor a pole. No, f can have a pole, right? If f can obviously have a pole. For example, if I choose the function, let's say, probably I can choose 100 over z. right? Then it will omit plus or minus 10 because we have mod of z is less than 1, greater than 0 and less than 1, right? You can search for a function yourself as well, it won't cost, but conceptually what we can find is that the only thing which it cannot have an essential singularity there. It can also have a removable singularity there as well. You can just choose f to be identically 0. So a, b and d are wrong. So let us move on to the next question. The next question says that let d be a disk. Okay, d is the unit disk, d closure is the closed disk, closed unit disk. It's a continuous function. Okay, and f on d is holomorphic. Okay, so f on the disk is holomorphic, it's continuous at the boundary, so it's holomorphic on the closed disk. Fine. And f vanishes at exactly one point a inside d, and we are given that a is some point from the open interval -1 to 1, and f at 1 is again 1. Find all the functions which satisfy this particular property. Okay, now something which you can observe is the following. So there were a lot of informations given in the problem in the following sense. First of all, see that the function f, it's holomorphic on the closed interval d. It shouldn't be holomorphic on d, I'm sorry. Okay, so yeah, again I again made a mistake, and for that let me give the alternative. So a misconception which you should keep in mind, that for a function f to be holomorphic, at least you can relate it to this scenario, on a closed set K, it must be holomorphic on some open set U containing K, which is obviously not the case here. So I cannot claim that f is holomorphic. Nevertheless, it do not require f to be holomorphic on the closed set D closure, but something which I can see from here clearly, that by the maximum modulus principle, since modulus of fz is equal to 1 for all z in the boundary, modulus of z must be less than or equal to 1 on D, right? So therefore f is an automorphism of D, right? F is an automorphism of D. So f of z must clearly be of the form z minus a over 1 minus a bar z, right? And in fact, is there something more which we are given to? So it vanishes exactly at one point. We just choose that point itself, because 1 over a bar will not be here, so it's analytic there. And for categorization, what I can typically try and do is that for f of 1 to be 1, what more can I say? F of 1 equals to 1, what would that imply? 1 minus a over 1 minus a bar is equal to 1. So 1 minus a is equal to 1 minus a bar, which implies that a is equal to a bar. So a is a real number. So a is real. And that is something which is already given to us, that a is contained in the open interval -1 to 1. So it's actually real. It's given to us. But the final categorization would be that you can choose any integral power of this. and the reason why you can choose any integral power of this is the reason that a is contained within the interval -1 to 1. Okay, getting my point? Fine. So the categorizations should be the categorization should be z minus a over 1 minus az, because here now a bar is equal to a whole to the power n. So you can categorize them in this form. Okay, let us quickly move on to the next problem. Let f be a non-constant holomorphic function on the disk D for this f, you are given that there exists a holomorphic function g on t such that f is equal to e to the power g. There is a unique g. No, it's not unique immediately from the fact that exponential is 2 pi I periodic. So it's obviously not unique, because if f is equal to e to the power g, then it should also be equal to e to the power g plus 2 pi I. For any f as described above, f of d is necessarily simply connected. If we choose f of z equal to e to the power 5z, then it's no more simply connected. For it to be simply connected, it needs to be path connected and it needs to be contractible, but it will always have it will always have a hole at 0. It won't be simply connected. Okay, so f of d, this won't be simply connected. Okay, let us quickly move on to the next problem. Okay, so this is a very fine problem and I'm just giving the hint to it. From the immediately from the integral itself, you know that it's the argument theorem which you require. Okay, f of z here given to you is e to the power pi over 2z minus e to the power minus pi over 2z. Something which you can immediately claim from here is this has no poles, so the argument principle can be immediately applied to only the zeros. We know that 1 over 2 pi I integral over c f prime of z over f of z, when each of the zeros and each of the poles have winding number 1, this is nothing but the sum over the number of poles, number of zeros, or just the zeros because we have the winding number 1 minus the number of poles in C. And this is having no zeros, so it's not having any poles, not zeros, any poles. So the only thing you need to check is what are the zeros here. And if you take e to the power pi over 2z minus e to the power minus pi over 2z equal to 0, then you get e to the power pi z is equal to 1. And from here, what can you conclude? So if this is the case, then I'm sorry. From here, you just need to solve this. So it's e to the power pi z equal to e to the power 2 pi I k. So from here, z is of the form. So pi gets cancelled out, 2 I k, right? So all the singularities are exactly on the imaginary axis. And what are those? So you will have z to be, let's say k starts from 1. So you have 2i, 4i, 8i, and so on. And you need to get till, so you have the disk of radius 2023. So you will get till 2023i. See, the disk is of this form, right? So here you have 2023. It was centered at 0, isn't it? Yeah, you have minus 2023 here. Observe that you will get here exactly 1011 such zeros. You will get here exactly 1011 such zeros, because whatever the number of zeros will be here, by symmetric nature it will also be reflected back here with a negative sign. And if you include back the trivial zero, which is 0 itself, you get a total of 1011 plus 1011 plus 0 plus 1, which is 2023 zeros itself. So the answer should be just 2023. Let us move on to the next problem now. So okay, so this is the problem which I was saying that you'll get a repetition in the problem. See, this is the same problem as the first question was. You are given the power series in terms of some center. You are given an expansion with terms of in terms of another center. So what you typically need to do is that you need to analyze whether you get any singularities in terms of the other expansion given to you, and just find the shortest distance between the singularities and the center. Okay, now see this here, you have s equal to 1 plus 2z plus 3z square and so on. Therefore z times s can be written as, you can just take z and just shift it out. So you get z plus 2z squared and so on. If you just subtract it, so you get 1 minus z times s equal to 1 plus z squared and so on. So this is 1 by 1 minus z. So therefore z just comes out to be 1 minus 1 minus z whole squared, right? So the singularities are only 1. I mean it's repetitive, but it's only 1. So and the center here is 2. So therefore the radius of convergence should be 2i minus 1 and the modulus of it. That is nothing but root 5, right? So this should be your radius of convergence. Let us move on to the next question. What is it said? So let f of z be an analytic function in an open set of the complex plane containing the closed unit disk D. Let m be the minimum of the set of the set of all absolute values, and capital M be the minimum of the set of all absolute values. Okay, C is the boundary, which is the circle itself, because you are given the closed unit disk. Assume that the minimum and the maximum are different. Okay, fine. We are just said that they are not the same, that it's not a constant function. Fz admits a 0 in D. Okay. Yeah, let's think about the problem. Okay, let us go through the question once more. We are given that f is an analytic function on the on an open set on the complex plane containing the closed unit disk. Okay, so let me just draw it once. I have the closed unit disk. It's analytic on an open set which contains the closed unit disk. M is the minimum on the closed unit disk. A capital M is the maximum on the closed unit disk, and C is the boundary, and we have small m is less than capital M. Okay, now observe that if small m is strictly less than capital M, what can we conclude? Doesn't that mean that the function is a non-constant function, which is the reason why small m is less than capital M, and the fact that the minimum is not attained on the boundary of the open unit disk, but it's contained somewhere inside. Are you getting my point? The analyticity of the function is given on, okay, sorry, let me just shade it with a different color, I'm sorry. So the analyticity of the function is given on this unit disk, not on the unit disk, on this open set. Are you getting my point? It's given on this open set, and we are being said that the minimum and the maximum are different, which means that the function is not constant. So the function is not constant, and also that the minimum is attained somewhere within the region of analyticity. So by the minimum modulus principle, there are only two possibilities. Either the function has to be 0 at some point within the region of analyticity, or it must be constant. It's not constant by the given hypothesis, so it must have a 0, right? So therefore f admits a 0 on D, and if z attains on D every complex value omega such that omega modulus of omega is less than m. Okay, how do we try this out? I think it will be true if z attains on D every complex value w such that the modulus of w is less than m. Okay, so see, f of z is equal to w. That is same as writing f of z minus w. So what are we being asked in option B is that whether this has a solution, right? But this will have a solution, isn't it? Because observe that modulus of f of z, this is how do we explain this? See, one thing which we let me be a bit clear. I'm actually trying to apply the Rouge theorem here, and the Rouge theorem needs to be applied on the boundary. The maximum is also obtained on the boundary. So if I'm talking over the boundary of the function, we're talking about the boundary of the function. I suddenly realized that I read the question a bit wrong. I'm extremely sorry, but whatever I did was right. So here capital M is given to be the minimum on the region of analyticity. I didn't read it wrong typically. The concept I kept in my mind was correct. I just read it out wrong. Here M I read it out to be maximum, but it is given to be minimum on the region of analyticity. Right. Whatever I said was right. Fine. Not no. I didn't conceptually took it to be wrong. I just read it out to be wrong. Yeah. So what I was saying is that I want to apply the Rouge theorem here. So how do I try this particular thing out? See, something which I can do is in the following sense. I need to find out number of solutions of this particular equation, right? If I have a solution here, then I'm good to go, isn't it? Then, so if I choose g of z to be omega, to be some omega, then that implies modulus of g of z is equal to modulus of omega, which is less than m, and m is the minimum of modulus of z. So this is the reason why I just came to notice that I read it out wrong. This must be less than equal to mod of z, right? So now I can apply the Rouge theorem. So therefore, by Rouge theorem, f and f plus g, which is equal to f of z minus w, have the same number of roots. But we in part A we concluded it out that f has a 0 in D. So this equation will also have a 0 in D, and therefore f of z equal to w at some set in D. So it will attain every complex value. Yeah, this was a good question. I just read it out wrong. I'm extremely sorry for that. I'm making this lecture. It's pretty dark now, and it's also pretty cold. So I'm not that comfortable at the moment. But nevertheless, passion wins, guys. Passion wins. Oh, fine. We are done with all the problems. Oh my goodness. Okay. Okay. One problem which I probably have missed, but it's actually a pretty easy problem. But I just thought of including it. So let me write the question once. After I write the question, I'll restart the lecture. Okay, so this was the problem, that let f from C to C be holomorphic. So f is an entire function. Suppose that f is bounded on the set which is given in this way. So it's sort of a triangular, an infinite triangular region. I just forgot the name. Sector. So it's given to be a sector. I'm sorry. It's given to be a sector. And it said that outside the sector, the real part of f is always greater than 0. What more can you say about f? And it's further added be specific. Now the solution to the problem just lies if you just draw the problem. I mean, the regions associated with the problem. So the first sector is nothing but, so it includes 0, and it ranges from pi by 4 to 7 pi by 4. So it's this particular sector. So this is S, and F is said to be bounded here. So what you can do is that you can particularly try and trace out a region like this. Okay, just in order to keep in your mind that F is bounded, so if cannot go beyond here, so F automatically leaves uncountably many points here. But nevertheless, F leaves uncountably many points on the whole complex plane, because the real part of f of z is 0 on everywhere outside this particular region. So if it's bounded like this and outside, f is, so the real part of f, so f is here. So f is in some sense like this. So what the only conclusion is that f leaves uncountably many points on C. So by Little-Picard's theorem, what can you conclude? The Little-Picard's theorem says that a complex entire function can leave at most one point. It cannot leave, it has the liberty to leave at most one point. So by Little-Picard's theorem, f has to be a constant, right? Is it clear? Got it? That should be your specific answer, right? Okay, so that's all for this lecture. In the upcoming lectures we will be coming up with some different topics for NBHM problem practice. Meet you guys until the next lecture. Thank you.